For nearly a century, cosmology has described a universe born in fire, expanding through space and time, dominated by unseen components. The lambda CDM model has been extraordinarily successful, but every model rests on assumptions. What if cosmic redshift has another origin? What if time itself is not what we think it is? This is the Exochronous Universe, rethinking cosmology from first principles. There is a number that tells us how fast the universe is expanding. It should be one of the simplest quantities in cosmology, but depending on how we measure it, we get two different answers. In the previous episodes, we explored the standard model of cosmology, lambda CDM, and the idea of cosmic inflation, introduced to solve several profound problems in the early universe. But despite its successes, modern cosmology now faces a new challenge. Different methods of measuring the expansion rate of the universe appear to disagree. The Hubble constant, h0, describes how fast the universe is expanding today. The farther away a galaxy is, the faster it appears to move away from us. In this equation, distance and velocity are directly related. Measure the distance to a galaxy, measure how fast it appears to move away, and you can estimate the expansion rate of the universe. But measuring that velocity is not as straightforward as it sounds. Astronomers infer it from the redshift of light, the stretching of spectral lines toward longer wavelengths. In the standard cosmological picture, this redshift is interpreted as evidence that space itself is expanding. There are two ways of measuring h0. The first method looks deep into the past, to the oldest light in the universe. Tiny fluctuations in this radiation preserve a fossil imprint of conditions in the early universe. In particular, they encode a characteristic physical scale, the remnant of primordial sound waves travelling through the hot plasma of the early cosmos. Using the lambda CDM model, cosmologists can translate this ancient pattern into an inferred expansion rate today. This approach gives a value of around 67 kilometers per second per megaparsec. The second method measures the expansion more directly by building what astronomers call a cosmic distance ladder. Astronomers first calibrate nearby distances using objects of known brightness, then extend those measurements farther and farther into deep space. By combining these distance measurements with observed galaxy redshifts, they obtain a second value for the expansion rate, around 72 to 74 kilometers per second per megaparsec. These two values do not agree, and the discrepancy is now far larger than the expected experimental uncertainties. This is no longer considered a minor measurement issue. It has become one of the most significant unresolved problems in modern cosmology. But beneath this tension lies a deeper conceptual issue. In the standard cosmological model, the Hubble constant is not something derived from first principles. It is a parameter we measure today, and then use the equations of cosmology to reconstruct the past. In other words, the expansion rate of the universe is not predicted by the theory, it is inferred from observation. A complete theory of the universe, ideally, would do more than fit observations. It would explain why those numbers take the values they do. And that raises an intriguing possibility. If different methods disagree, is the problem merely in the measurements, or could it reflect something more fundamental about how we interpret what we observe? Cosmologists have proposed many possible solutions. New forms of energy in the early universe, additional relativistic particles, subtle calibration errors, even modifications to gravity itself. But so far, no single explanation has resolved the tension completely. There is, however, another way to think about the problem. Both methods assume that the physical scales we use to measure the universe and the clocks by which we measure time remain fundamentally constant. But what if they're not? What if the disagreement isn't entirely about expansion, but about how we interpret redshift itself? To understand the Hubble tension, we first need to understand a deeper question. What is cosmic redshift really telling us?